Welcome back. Today we're diving into Retrieval Augmented Generation, or RAG, one of the most practical techniques for improving LLM outputs.
RAG addresses a fundamental limitation of language models. They can only use knowledge encoded in their parameters during training.
With RAG, models can access external information at inference time, leading to more accurate, up to date, and grounded responses.
Let's start with the basics. What is retrieval augmented generation?
RAG is a technique where you retrieve relevant documents or passages from a knowledge base and provide them to the LLM as context before generating a response.
Instead of asking the model to answer from memory alone, you give it source material to reference.
This is similar to how humans answer questions. We look up information rather than relying purely on recall.
The process has two main steps: retrieval and generation.
First, you convert the user's query into a search query and find relevant information from a database.
Second, you feed the retrieved information along with the query to the LLM, which generates a response grounded in the provided context.
Let's break down the retrieval step. How do you find relevant documents?
The most common approach uses vector databases and semantic search.
You first embed both your knowledge base documents and the user's query into a vector space using an embedding model.
Embeddings for retrieval are typically created by specialized models like Sentence BERT or more recent models like E5 or BGE.
These models map text to dense vectors where semantically similar texts are close together.
Once you have embeddings, you search for the documents whose vectors are most similar to the query vector.
This is usually done with cosine similarity or dot product as the similarity metric.
For large knowledge bases, you need efficient search. That's where vector databases come in.
Vector databases use approximate nearest neighbor algorithms like HNSW, which is Hierarchical Navigable Small World Graphs, or FAISE, which stands for Facebook AI Similarity Search.
These allow fast similarity search over millions or billions of vectors.
Popular vector database systems include Pinecone, Waviate, Qdrant, and Chroma.
Now, once you've retrieved relevant documents, how do you incorporate them into generation?
The simplest approach is to concatenate the retrieved passages with the query in the prompt.
You might format it like context retrieve passages, question user query answer.
The LLM reads the context and generates a response based on it.
This grounds the response in the provided information, reducing hallucination.
Let's talk about chunking strategies for the knowledge base.
You typically don't embed entire documents. You break them into chunks, paragraphs, or fixed size segments.
Chunk size is a trade off. Smaller chunks are more precise but might lack context. Larger chunks provide more context but might be less focused.
Common chunk sizes are 200 to 500 tokens, with some overlap between consecutive chunks.
Overlapping helps ensure important information isn't split across chunk boundaries.
You also need to decide how many chunks to retrieve. Too few, and you might miss important information. Too many, and you waste context window or confuse the model.
Typical values are 3 to 10 chunks depending on chunk size and context window.
Let's discuss query reformulation and enhancement.
Sometimes the user's query isn't optimal for retrieval.
You can use the LLM to reformulate the query, expand it, add keywords, or rephrase for better retrieval.
Another technique is high DE, which stands for hypothetical document embeddings.
You prompt the LLM to generate a hypothetical answer to the query, then use that generated text for retrieval.
The idea is that a hypothetical answer might be more similar to actual relevant documents than the query itself.
This can improve retrieval quality, though it adds an extra generation step.
Let's talk about re ranking retrieved results.
The initial retrieval using vector similarity might not perfectly order results by relevance.
Re ranking uses a more sophisticated model to rescore the retrieved passages.
Cross encoders are commonly used for re ranking. They take both the query and passage as input and output a relevant score.
Cross encoders are more accurate than biencoders used for initial retrieval, but they're too slow to run over the entire database.
So the typical pipeline is fast bi-encoder retrieval to get candidates, then cross-encoder re-ranking of the top results.
Now, how do you evaluate RAG systems?
You can measure retrieval quality. Are the right documents being retrieved?
Metrics like recall at K or mean reciprocal rank assess whether relevant documents are in the top results.
You can also measure generation quality. Is the final answer accurate and helpful?
And groundedness is the answer supported by the retrieved documents, or is the model still hallucinating?
Let's discuss citations and attribution.
A well designed RAG system should cite its sources,
You can prompt the model to include citations, like according to document X year.
or use post processing to match answer segments to source passages.
Citations let users verify information and build trust in the system.
They also help with accountability. You can trace where information came from.
What about updating the knowledge base?
That's one of RAG's key advantages. You can update the knowledge base without retraining the model.
Add new documents, embed them, and they're immediately available for retrieval.
This solves the knowledge freshness problem. LLMs trained on data from 2023 won't know about events from 2024, but a RAG system can.
You can also remove or update documents to correct errors or remove outdated information.
Let's talk about hybrid retrieval approaches.
Pure semantic search sometimes misses exact keyword matches or named entities.
Hybrid retrieval combines vector search with traditional keyword search like BM25.
BM25 is a ranking function that scores documents based on term frequency and inverse document frequency.
You might retrieve using both methods and merge the results, or use one to re rank the other.
This captures both semantic similarity and lexical matching.
Another consideration is metadata filtering.
Your knowledge base might have metadata dates, authors, categories, etc.
You can filter retrieval based on metadata, for example, only retrieve documents from the past year or from a specific source.
This helps narrow results to relevant subsets of the knowledge base.
Let's discuss challenges with RAG.
First, retrieval errors. If the right information isn't retrieved, the model can't use it.
Second, context length limits. You can only fit so many retrieved passages in the context window.
Third, distraction from irrelevant information. If some retrieved passages are off topic, they might confuse the model.
Fourth, latency. Retrieval adds overhead, potentially slowing down response time.
And fifth, cost. Embedding, storing, and searching large knowledge bases requires infrastructure.
Let's talk about advanced RAG techniques.
Iterative retrieval involves multiple rounds. The model generates a partial answer, which is used to retrieve more information, refining the answer.
This is useful for complex queries that require assembling information from multiple sources.
Agentic RAG treats the model as an agent that decides when and what to retrieve.
The model might first try to answer from memory, then retrieve if uncertain, or retrieve specific information as needed.
Graph based RAG uses knowledge graphs instead of or in addition to text documents.
The model can traverse relationships in the graph to find connected information.
There's also cross encoder in the loop RAG, where the generation model and retrieval are tightly integrated.
The model might request specific information, and the retrieval system responds to those requests.
Let's discuss RAG for different domains.
RAG is widely used for question answering over enterprise documents, customer support knowledge bases, and research paper search.
In medicine, RAG can ground diagnoses or treatment suggestions in medical literature.
In law, it can retrieve relevant case law or statutes.
For code generation, RAG can retrieve similar code examples or API documentation.
Finally, let's talk about the relationship between RAG and fine tuning.
They're complementary approaches. Fine tuning bakes knowledge and behavior into the model. RAG adds external information.
You might fine tune a model for a domain or task, then use RAG to provide specific current information.
For example, fine tune on medical reasoning, then use RAG to retrieve the latest research.
Some systems combine both for optimal results. The model has domain expertise from fine tuning and specific facts from RAG.
So, to recap, RAG retrieves relevant documents and provides them as context for generation. It uses vector databases and semantic search for efficient retrieval. It grounds responses in sources, reduces hallucination, and enables knowledge freshness, re ranking, and hybrid retrieval, improved retrieval quality. And it's complementary to fine tuning for building robust applications.
Next episode, we're exploring multimodal transfer, extending LLMs to handle images, audio, and other modalities.
Thanks for listening.
Until next time, keep learning and stay curious about